All right, now I'm talking about amide bond coupling. So we're gonna basically go from a carboxylic acid over to an amide species. So what that's gonna look like is we're gonna start with our carboxylic acid. The first thing about our carboxylic acid is that it is acidic, crazy. So we're gonna essentially try to use this oxygen, which is gonna turn into a carboxylate, so it'll have a negative charge. We're gonna try to turn this into a nucleophile. Now we're gonna start off by basically pairing with any base. And we're gonna have, so we're gonna use the base, which is pyridine here, and then we're gonna use DCC, which is dicyclohexyl carbodiamide. Here it is. It is a structure half. And then we're gonna have our amine species that we're looking to attach. I'm just gonna do H2NR because that's easy. So the first step, obviously, we have an acid, we have a base, deprotonated our acid. And I'll get into the nitty-gritty of why we're using dicyclohexylcarbodiamide, also called DCC. Essentially, so we need to think about the charges on this now. So nitrogen is electronegative compared to carbon, so we're gonna have partial positive charge on carbon and partial negatives on the nitrogens. What's important is the partial positive on the carbon, because when we get this, we're gonna get a nucleophilic attack. And we create this really weird complex. What's important for us now is that we need to stabilize this. So luckily we have our conjugate acid from our base that just has a proton sitting here. And this nitrogen that's negatively charged, this is a net stabilizing movement because we have getting rid of the anion. So now we have okay. So now what we want to do is we want to tag in our nitrogen. But before that, I want to mention real quickly what drives this reaction. Essentially, we have our product. Our side product is just something called dicyclohexylurea, which looks like this. Dicyclohexylurea. That's what a side product is. Let's call it DCU. So we need to try to get to this because this thing is not, it's not soluble in organic solvents. So this precipitates out and it's extremely stable. So what we need to do is we need to get closer to there from here. So first thing is that this is pretty stable overall. So we need to now attack with the nitrogen onto this carbonyl. Cool stuff. And now we have I'm being very particular with how I draw this. Oops. Cool. So this is positively charged, this is neutrally charged. Essentially, you can get like an internal proton transfer essentially. And this transition state has 6 members, I think. 1, 2, 3, 4, 5, 6. So in terms of reaching it, it's not too far away. So this nitrogen right here can function as a base, deprotonate this other nitrogen. And we get sorry, don't be so cursed. There we go. Alrighty. Now we're here. And now we're extremely close to our final product. As you can see, we are like, this is like what's about to form our dicyclohexylurea right there. All we need to do is make this thing leave. It's a good leaving group. And what we just do is kick it down. This bond will go here, forms that pi bond. This pi bond breaks, neutralizes the nitrogen. And we have our product and a side product. This is tiny. Dicyclohexylurea. And this is our amide right here. This is what we want. Just remember that this is our target, and we came from a carboxylic acid, DCC, a base, and the amide that we wanted to attach.